Alright, hopefully the phone won't ring again this time. I don't have to start all over. If it does, I'm probably just going to keep going. So, Chapter 11, Section 1 is all about volume and mass relationships. We've done the stoichiometry with mass and moles and mass and, moles and things like that. So now we're just going to throw in volume. And the first little thing that we have is another contribution from our favorite little Frenchman, Gay-Lussac. He came up with that if you have a reaction, so like let's say we have the production of ammonia. Whoa, I didn't get a pen. Sorry. Okay, how about the production of water? And you keep this whole reaction at a constant temperature and constant pressure. Well, these coefficients, the little imaginary one right here, yeah, we know of them right now as mole ratio. So like for every 2 moles of hydrogen, we're going to have 1 mole of oxygen react. But if temperature and pressure are kept constant, you can also say every 2 liters of hydrogen will react with 1 liter of oxygen. And so that looks like that. If you imagine that each of these little ball things is 1 liter, see that 2 liters of hydrogen plus 1 liter of oxygen will give us 2 liters of gaseous water vapor. So let's say we have our water reaction, and I want to know how many liters of hydrogen must be used to react completely with 12 liters of oxygen, and we are assuming a constant temperature and pressure. So that means we get to use our coefficients as volume ratios, the same as we get to use them as mole ratios. So we start with what we were given, 12 liters of oxygen. Go up to our equation. It's a 1:2 ratio, so for every 1 liter of oxygen, we are going to need 2 liters of hydrogen. So liters of oxygen cancel out, and you're left with 12 times 24, or sorry, 12 times 2 is 24 liters of hydrogen gas. Remember, this only works if you are at constant temperature and pressure. If temperature or pressure is changing, then you don't get to do this. So just another example here, how many moles of O2 are needed to make 24 moles of water? So again, we start with what we were given. Whoa, I didn't mean to put moles here. I meant to put liters, so let's just go ahead and change that. Doesn't matter though, it's all the same math. So 24 liters of water, vapor. Keep in mind this is water vapor, not liquid water. So put a little gas here if you want. And the mole ratio, or the volume ratio, is 2:1. So for every 2 moles of water vapor, we're going to need 1 mole of oxygen gas. Oh gosh, I'm doing it again. Not moles, we're talking about volume here. So liters of water, and we just work out 24 divided by 2, 12 liters of oxygen. Then you got Avogadro, and he's the guy that we get to credit for coming, or he's named after this right here. That's not negative. 23rd, and this is like particles per mole. Usually we would say like that many atoms per mole, or that many molecules per mole, or that many objects per mole, but you just generally say particles. What he came up with was that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. So, at the same temperature and pressure, volume varies directly with the number of moles. Or you could say V1, sorry, let me rewrite this. V1 over N1 equals V2 over N2. Like that. Looks just like the Charles's law and Gay-Lussac's law, except now instead of temperature and pressure, we are throwing in number of moles. So that leads us to this thing, the molar volume of a gas. It's just like molar mass, except for its volume. It's the volume of 1 mole of a substance. And because Avogadro's law states that 1 mole of gas has the same number of molecules, same volume as any other gas at the same temperature and pressure. Oh, sorry, that went a little fast. 1 mole of gas, same volume as as any other gas. Doesn't matter what the identity of the gas is. Doesn't matter if it's big, fat, heavy CO2 or little teeny tiny helium. They're all going to have the same volume. So if we want to standardize this, then we can use the magic STP. And if we say standard molar volume of any gas at STP, the magic number is 22.4 liters. And the lab that you guys did yesterday was meant to prove that molar volume. They will still have different masses though, because we do still have big fat heavy gases like CO2 that has a mass of 44 grams per mole, and we have little bitty teeny tiny hydrogen gas that has a mass of 2 grams per mole. And just to refresh your memory, STP is 1 atmosphere and 0 degrees Celsius. So this is where I'm showing different masses but identical volumes at STP. And these are some actual experimental data. Here would be the one that we did right there. We generated hydrogen gas. And as I was looking over some of y'all's work that y'all did today, y'all got really low % errors. And that's because this 22.4 is the real deal. It is the standard molar volume of gases at STP. So, chemical reaction takes place. That produces 0.068 moles of oxygen. What volume in liters is occupied by this gas sample? And here's our key phrase. At STP means we get to use 22.4. If we were not at STP, then you cannot use 22.4. But because we are, we get to do stoichiometry. So 0.680 moles of O2, and we need to convert that to volume. So for every mole of oxygen at STP, we're going to have a volume of 22.4 liters. So that cancels out, and you take 0.0680 times 22.4, and you end up with, incorrect sig figs, 1.52 liters of oxygen. Another chemical reaction produces 98 milliliters of sulfur dioxide gas. Key phrase, at STP, that means we get to use 22.4. What was the mass of the gas made? So we're going to start with our volume, 98.0 mils of sulfur dioxide. And these are milliliters. Remember, molar volume is in liters. So the first thing we need to do is convert to liters. That looks like that. And then we get to use molar volume. 22.4 liters are contained in every mole, and then each mole will have a mass of 64.07 grams. That's the molar mass of sulfur dioxide. I didn't need all this leftover line. And you plug this in, 98 times 64.07, and then divided by 22.4 divided by 1,000, and you get 0.280. So the mass of the gas that was made was 0.280 grams sulfur dioxide. If you cross things out, milliliters is gone, liters is gone, moles gone, grams, SO2. Those are our final units. And just to kind of reiterate what I have done here, whenever you start in volume and you are at STP, and the question asked you your mass, this is just a typical stoichiometry problem, except instead of starting in grams like we have been, we're starting in volume. Okay, another example. A chemical reaction produced 3.1 grams of CO2 gas. What volume will it have in milliliters at STP? That means I get to use 22.4. I keep reiterating this because, yes, there will be a point where you don't have STP. So we start with the number that we were given, 3.1 grams of CO2. And because I'm starting in grams, and that means the first thing I have to use is molar mass. So the molar mass of CO2 is 44.01 grams per mole. And because I am at STP, I get to say that 1 mole has a volume of 22.4 liters. And the question asked me for my answer in milliliters, so go ahead and make that conversion. Alright, plug this into the calculator. 3.1 times 22.4 times 1,000 divided by 44.01. is 1577. I can make that 1578, and we're only allowed 2 sig figs, so actually just 1600. And that is milliliters of CO2. Okay, I have a fourth example here, but I'm actually out of time. So, if you need to see it, come on in and see me, and I'll see you guys tomorrow. Be ready for anything.